My name is Namita Lokare, and I work for a local startup in Austin. And today, I'm going to be talking about AI and wearable devices. So this project started off at North Carolina State University, where I got my Ph.D. from, and we recently submitted a journal for this work. These are my collaborators from NC State, and this project was funded by the NSF through the Assist Center. So let's get started. How many of us remember this device? This is March 2003, and you have this gigantic device on your hand that could tell you your speed, how many miles you have covered. How about this one? This was September 2012. And today we're here. We've come a long way. In the span of 15 years, we've seen tremendous growth in technology, not only in the hardware, but also in the software. And we've seen this growth not only in smartwatches, but we've seen similar growth in other industry, in other wearable devices, such as earbuds, you have smart textiles, you have shoes, you have wristbands. And all of these devices are collecting information about your physiological responses, such as heart rate, your breathing rate, and also your kinematic information, such as your tracking your activities. And there's so much data that's coming in, and there's so many correlations that one can make. So, and we can learn more about our bodies by using these devices. So let's look at some of the numbers of how many devices are being used. So this was a survey that was released by Gartner, and they categorized devices. They actually had forecasts for the shipments of wearable devices worldwide in millions of units. And if you see in 2019 alone, the shipment for the smartwatches is going to be about 130 million units, which is supposed to increase in 2022 to about 190 million. And we see similar trend in other head-mounted displays or smart clothing and ear-worn devices as well. So who's using these devices? So Statista Global Survey released a survey in July 2018, and they categorized users by age. And if you look at the numbers, you see that everyone is using these devices, not only from the age group of 18, but towards the age group of 65 as well. And this drives the point that even though it's like newer technology, the older generation and the newer generation are all adopting this to become more aware of their health. And they also categorize users by gender. And when they did that, they saw that there was the numbers look great. And not only the female users are using this, but also the male users are using it. So as data scientists, we often come across this question that we have so much data, what inferences to make, how to unravel some of this data, how to design algorithms to come up with solutions that can give users good feedback. And we were faced with the same question when we decided to work on this project, because we had data coming in from a lot of devices, from the environment, from your physiological data, and also your accelerometer, so kinematic data. And we did a lot of research, and in order to make more of higher level inferences, we decided to start off with the basics. And those were some of our main reasons why we decided to do this project. So we decided to do activity recognition to start off, and then use these inferences of what activities you're doing to then make higher level inferences. So for that, we needed some data. So meet Jimmy here. He is a graduate student at NC State who helped us with some of the data collection. And so we put a bunch of sensors on Jimmy and made him do different activities and used his data to prototype some of our algorithms. And this is how Jimmy's data looks like. So you can see you have joint data, you have accel, you have heart rate from this data, and we're constantly collecting all this data. But we were like, okay, how do we go from here to telling if Jimmy's biking, right? So we decided to use two tools, one from topological data analysis and the other from signal processing called time delay embedding to design our algorithms. And so before I dive into how we use those tools, let's learn what those tools are. So topological data analysis learns the topology of a space. That means we're interested in the structure of the space, which is preserved under deformation such as shrinking, stretching, but not tearing or gluing. So we're interested in the structure of M here. M, you can imagine it's a manifold, which is locally Euclidean. But in real life, we have access to M only through X, which is a subsample version of M. So we want to learn the structure of M through X. And topological data analysis allows us to do that by using combinatorial objects such as simplicial complexes. So a zero simplex is a dot or a point. One simplex is 2 points connected by an edge. A two simplex is 3 points connected by edges in between them, and so on and so forth. Topological data analysis uses something called as filtration. A filtration is a sequence of increasing subsequences. So we start off with every point in X, and we look around. We start off with an epsilon ball around X, around each point in X. And we grow that ball as we go on. So at epsilon 1, we see that as we grow this ball, the neighboring balls intersect with each other. And when they do that, we connect edges in between them. Or if two or more intersect, we connect a triangle between them. And we keep increasing the size of this ball. At epsilon 2, we keep increasing it, and we see more edges being born. And at epsilon 3, we have everything connected. And this is what a filtration is. And this filtration is captured in something called as a persistence diagram. A persistence diagram is a diagram of the birth and death of these features that you see. And more specifically, we're talking about the dimension 0 feature and the dimension 1 feature. There are higher dimensional features as well, but for this project, we were only interested in the dimension 1 feature. And I'm going to tell you dimension 0 just for completion. So what is dimension 0? Dimension 0, we're interested in learning about the connected components in this structure. So if you look at epsilon 0, you have a lot of connected components. And if you look at the persistence diagram here, you can see that if you look at the persistence diagram here, you see the green clusters there are born at epsilon. So we have all the points in X are connected components at epsilon 0 in that persistence diagram. And if at epsilon 1, you see some of these connected components die, and ultimately we have 2 connected components left. And at epsilon 2, we have 1 connected component. Similarly, at epsilon 3, we have 1 connected component, which persists till infinity. So that's dimension 0 feature. Dimension 1, we're interested in number of holes in this structure. So we look at epsilon 0, there are 0 holes. At epsilon 1, we see that there was a small hole that was born, but it died really quickly. At epsilon 2, we see that in the center, we have 1 hole, which then dies at epsilon 3. And that's what's captured in this diagram there. We have a hole that was born at epsilon 1, which died really quickly. That's why you have a red dot near the diagonal. But at epsilon 2, we have another hole that was born, which died at epsilon 3. So these are the features that we're interested from our activity data, right? And so you may remember this representation of a persistence diagram, something similar to as a dendrogram, right? So if you look at the epsilon 0, the dimension 0 features, and if you plot a dendrogram, it will look like this, where a lot of clusters were born, then they get merged at epsilon 1, and then further get merged at epsilon 2, and then you have 1 cluster that's left. So this is something that people are familiar with. There's another interesting property of persistence diagram is the stability of these persistence diagrams. What I mean by that is if you have a data set M and its noisy sample data set X, if we compare the persistence diagrams between the two, then the distance between these persistence diagram is bounded by the distance between M and X. What that means is if you have noise, we're still guaranteed to have persistence diagrams that are bounded by a certain distance. So the next question is, how do we generate these point clouds, right? We know how to get from this X, we know how to extract features from this X, but how do we get to X? Because our data looks something like this. It looks like joint data. So what the next tool that I'm going to talk about is called as time delay embedding. And that will allow us to get to X, and then we can extract features from X. So time delay embedding is a method that is used in dynamical systems. And for example, if you see, we have 3 equations on this, and these equations, if you use them and simulate data evolving over time, you will get something called as a chaotic Lorentz attractor. But in reality, we only have incomplete measurements sometimes. And so say you have this only time series generated only from this first equation of the Lorentz equations. So how do you reconstruct the attractor from just this incomplete measurement? Time delay embedding allows us to do that by embedding and delaying this signal to generate something like this. And so this looks way a lot similar to what the actual chaotic attractor is with some noise, but the structure is preserved. So the equation to do this is this. So you have your time series, you need a delay to delay this time series, and then you need an embedding dimension that you can take this time series and embed it in. And once you do that, you will create an attractor, as you've seen before. But one has to be very careful when they pick what the embedding dimension is and what your delay is. As Mariam pointed out in her last talk, that if you choose too large of an embedding dimension, the complexity of this problem increases and it's going to be computationally expensive. If you pick a too small of an embedding, the reconstruction is not going to be accurate. And same with the delay. That's the tau in this equation. If you pick too large of a tau, you will have uncorrelated samples. And if you take too small of a tau, you'll have extremely correlated samples, right? So you have to be careful in picking up your tau and embedding dimension. Okay, so that's all about the theory. That was a lot. Let's put it to use. Let's test it on Jimmy's data. How does it look like? So this is how the delay embedding point cloud looks like when we do delay embedding on Jimmy's bicycling data. And all we do that is, to get to X, we subsample this point cloud, and then we have something similar to a point cloud like X. And then we know the drill. Once we have this point cloud, we do topological data analysis, and we extract these features. So let's put everything together. Let's do the pipeline. What we do is we take these time series data, we do dimension reduction. So we do a principal component analysis and choose the dimensions that explain 95% variation in our data. And then we pick 10-second windows over this data. We project them, and then we compute the delay embedding on that. We subsample this point cloud by using a Max-Min subsampling method. This method is a density-based subsampling, so the higher the density in a region, the more the points we're going to pick up from that region. And then we do topological data analysis, and we extract this most persistent feature, which is the largest feature, the feature that has the largest distance from the diagonal. And we concatenate all these features, and then we give it to a classifier. Here we're using the k-nearest neighbor classifier. So once we do that, we saw for different activities how these different features look like. And so we compared what happens during bicycling when we have a sensor on the leg and a sensor on the hand, and we saw that these features were very different for different activities, which makes sense because when you're bicycling, you have a larger periodic motion in your leg. When you're golfing, you'll have a motion in your hand. Similarly with waving and walking. So we extracted all these features, and I wanted to see how these features look when how these features actually look. Are they even separable, or are they even can we train a classifier? So this is what it looks like. We took all these features and we projected them to a three-dimensional space, and we colored them with their ground truth labels. So if you see, these features look separable, they're really clean, and if we train a classifier on this, then we're going to get a perfect result, right? So these are some of the results on the test data. So this is a confusion matrix, which basically tells you how your algorithm performed. And so the top column is the ground truth, and then the vertical column here is what the algorithm predicted. So we see that the diagonal has a really bright region, which says that, yes, the algorithm predicted that you were bicycling when it was bicycling, and golfing when you were golfing, and so on and so forth. We also note that there was you see this bright area where waving and golfing had some misclassifications, and we figured that when you're golfing and your waving motion have some similarities, and that's why those misclassifications were happening. So now you'll say, okay, this data set is super clean. You saw the features, they were really clean. But in real life, nothing is that clean. So we also tested this on accelerometer data, and we added some more complex activities. By complex, I mean there were two activities in one. For example, carrying a box. So in that activity, you're holding something, but you're also walking. So we saw that for periodic activities, our algorithm performed really well. But for some complex activities, like carrying a box, we had classification that had walking, and then some of them had something like carrying a box and then bicycling too. And so for that, we understand that this method has some shortcomings, such as if your periodicity in your motion is lost, if you have something random you do, this method will not pick that up. But for some complex activities, we still pick up the simpler activities on those complex activities, right? Okay, so this is the same pipeline that you've seen before. This is the pipeline for recognition. And if you recollect, I talked about subsampling the point cloud. And when we subsample the point cloud, we're subsampling based off of densities. So if sometimes, if the density during in one region was higher, we pick more points from there, and so on and so forth. This method had some shortcomings because in real time, when data is streaming, sometimes the sampling rate changes, sometimes you have noise, and so there were, because of density-based methods, these point clouds that were subsampled were having noise. And so the features from the persistent diagram were lost. So we decided to improve on this particular method so that it's faster and it can be used in real time. So this was the data that we took from the right knee and the left wrist, and we created a delay embedding. And as you can see this in the center, you have this structure where you have this squiggly line in between, but the actual structure is more of a rectangle. So this is a noisy outlier in our structure. And if we did a Maxmin subsample as density-based, we end up picking up samples from the outlier trajectory. And if then we do persistence diagram, those features are lost because we get multiple cycles in between, multiple holes in between. And our misclassification rate increases. So we introduced something called as TRED, which is a trajectory-based density estimation method. And it looks at how many trajectories are passing through a region. So we tessellate the space, and we look at how many trajectories are passing through a given region. We count them, and if they pass our threshold, we say, yes, this is a valid sample, so pick samples from this region, and so on and so forth. right? So we do that, we do the same thing, and now you can see like, because there was an outlier trajectory, we didn't end up picking up samples from that by doing this tread method. And then our feature is just one hole that was, that lived, which is representative of the structure of this method. So another example I wanted to show, this is an ellipse where it's a synthetic ellipse. The red structure around it is actually an ellipse, but we have an outlier trajectory that goes inside the ellipse. And if the ground truth persistence diagram for this is just this feature here, if we did maximum subsampling, which is the density-based method, we end up picking up samples from inside, and thus the features are lost. And then with tread, because it's a trajectory-based method, it ends up picking up the most trajectory density-based samples. So putting that back to the pipeline, we replaced maximum subsampling by tread, and we realized we increased the speed by 18% here while maintaining some of our performance levels too. Okay, so now the question is, what do we do with these activities? We know that you're walking or bicycling, so how do we use this information to then make some higher level inferences? So I work for a company called Level, and at Level we are trying to bring hydration technology to smartwatches. What that means is we're trying to tell you how hydrated we are, or how are you hydrated enough to go into a workout, or how much water you should be drinking throughout the day. And you may say that, okay, this is a simple problem. Why do I need a device to tell me that I should be drinking water? My body's already telling me that I'm thirsty, and then I'll drink, right? But it's not that simple. When the body tells you that you're thirsty, it's already too late, because it's the body's response to avoid certain things from happening. So let's look at some of the things that are caused by dehydration. About 75% of Americans suffer from chronic dehydration. And it affects your mood, it affects your exercise levels, your performance decreases if you're dehydrated. You get headaches, it affects your sleep, it affects your energy levels, and it also affects your food intake. So one of the applications that we are looking at is fall detection. And we care about our loved ones, so we want them to stay on top of their hydration. And as research tells us that thirst weakens with age, we want something to we wanted to give people the ability to prevent these falls from happening instead of after the effect, right? So using some of these tools, we can better estimate the hydration needs, how much water you're losing, how much water you're taking, while performing all these activities gives us better understanding of what's your actual loss, right? So I wanted to conclude this talk by encouraging everyone to go out and drink some water and stay hydrated. Thank you so much for attending this talk. Stay hydrated.